All right, so this is topic 7.7, calculating equilibrium concentrations. Your objective today is to be able to identify the concentrations or partial pressures of chemical species at equilibrium based on the initial conditions and the equilibrium constant. So you're going to use stoichiometry. You can determine the K value, the K constant. You can determine the expression based on the products and reactants. And from there, you may be able to determine what is the concentrations or the partial pressures of each of our reactants and products based on the initial values. So with this, they don't exactly go to completion, so that's why they're existing both forwards and backwards. So products and reactants are both existing at the same time. So you're going to use something called an ICE table. ICE is for initial, C is for change, E is for equilibrium. So for example, you have A plus 2B produces 4C. These are all going to be in concentration, so that means we can use all three of these reactants and products in our expression. So what is the value for Kc if our initial concentrations for my reactants are 1 and 1 molar each? And the equilibrium concentration of C is 0.120 molar. You start by writing the reaction if not given, and then the K expression is start by filling in the table. So let's see. Our K expression is going to be K sub C equals C to the fourth over the concentration of A times the concentration of B squared. Since you have no information about the value of C for the initial value, we can assume that there's going to be none, so it's going to be 0. And then from there we can kind of figure out that, oh, hey, that means that my C, or my increased by 4C. So increased by plus 0.120 molar. Excuse me. So the change that's related to the change that's occurring is stoichiometry all through stoich. Okay, so we can use the mole ratios to figure out the other ones. So just so we're clear that my product increased to 1, so it's going to be 0 plus 4x, if you will. That's going to equal 0.120 molar. I'll take out that n. So you got to solve for x, so it's going to be 0.030. That means that all of these other things, A is going to decrease by x, and then my other reactant is going to decrease by 2x. Since my products, increased by 4x, so to speak. So if x is 0.030, I'm going to subtract that out from here, and I'm going to subtract 2 times that, so negative 0.060. Then I'm going to end up with 0.970 molar, and then 0.940 molar for my other reactants. We can find the equilibrium values, which we did, and then plug them into the equilibrium constant, so which we said was K sub C equals C to the fourth over A, then over B squared. So hopefully, something I would do math-wise, I would actually put my denominator in parentheses so I can make sure that it's keeping everything where it needs to be, so to speak. So I'm going to do 0.120 to the fourth all over 0.970 times 0. Oops. I'm actually going to make these all brackets because they're all concentrations technically. This is going to equal 2.42 times 10 to the negative 4. That's it. When I do the math, that's what I should get. In another example, we're provided with the K value and the initial concentrations that define the equilibrium concentrations. We use another ICE table. we have our reaction A plus B yields AB. And these are all aqueous, so we can all use these. We already have our equilibrium constant of 3.4 times 10 to the negative 3. If I have 1 molar of A and 2 molar of B, and their relative to reach equilibrium, what are the equilibrium values? Okay, so just so we're clear, I'm going to start by writing my reaction, which we already have, and the Kc expression. So that would be K sub C equals AB, the concentration, over A times the concentration of B. That's going to equal 3.4 times 10 to the negative 3, which are already given in the problem. That's why I know that. Here, I am going to see, how should I put this? Oh, actually, I'm so, since we know that there is no AB, we're going to assume it's 0. Since we know that we have some reaction going on, based on my K value, and it's considered small, we know that some product or a good amount of product is being formed. And since we don't know much else about it, we can assume that it is going to increase by X to make our final equilibrium concentration. If there are coefficients, like say 2AB or 3AB, we would know that it would increase by 2x or 3x. Then we can complete the equilibrium value in terms of x. So that means that because my A and B are also just one, there's only one for the coefficient, it's going to decrease by x for both. From there, we can figure out we can now plug in those different values that we determined and try to solve for the value of x. Oops. This is going to equal 3.4 times 10 to the negative 3. Okay. So there are two ways of solving this. We can plug into our calculator for graphing and using the solve function, which you'll get a handout for. Or because my K sub C is considered small, that means my x is also going to be small too because it's on my numerator especially. So we're going to assume is that the x's in my denominator are going to be negligible. And then we just solve for x, we end up with 6.8 times 10 to negative 3. You'll notice that these are very similar. That means it's okay to assume. So the times to assume that the x is going to be negligible is if the K sub C is a small one, meaning it's less than 0.001. After finding the value for x, we need to substitute it back into the equilibrium values. So once we realize that x is 0.0067, you'll notice by sig figs, not much is totally different. Okay? So if x is 0.0067, from there we can just subtract that from each of those, and we'll see that our concentration values didn't change by much. So once you figure out what x is, most likely you will need to plug that back in to solve for the equilibrium concentrations for each of your things that need to be solved for. All right, so if you have any questions, please let me know. For solving with a calculator for this part, solver function, if you will, graphing, please refer to the handout that you'll be given. Thank you.